Alright, good evening again, mathematicians. It's funny, in the last video, I realized that I said, work in your groups, but I completely forgot that you guys are going to the zoo, so you're not going to have your groups here. Alright, so when I say work with your groups, I mean work on your own, try it on your own, okay? Alright, so 3.3, here we have making a difference, connecting growth rate and growth factor. Now, how does the initial population, so notice the word here, initial population, we can also write the word initial value here, affect the growth patterns in an exponential function? And the vocab I have for you today is something called compound growth. This is just another name for exponential growth. And you'll usually see compound growth in like investment or banking situations. So we'll say usually seen in investment situations. Okay, but essentially they are the same thing. So compound growth versus exponential growth, no, they're the same thing. All right, here we go. So here's our problem. Mrs. Ramos started college funds for her two granddaughters. She gave $1,250 to Cassie and $2,500 to Kaylee. Sorry, Cassie. Mrs. Ramos invested each fund in a 10-year bond that pays 4% interest a year. I'm going to go ahead and highlight some important things. So Cassie gets $1,250, whereas Kaylee gets $2,500. Mrs. Ramos invested each fund in a 10-year bond that pays 4% interest a year. Now, really quick, 4%, is it a growth rate or a growth factor? Because it is a percentage, it is a growth rate, okay? So, question number 1 says to write an equation to show the relationship between the number of years and the amount of money in each fund. And look at that. We have we're going to let A equal the amount of money and N equal the number of years. So the growth rate. How do we change it from a growth rate to a growth factor? I hope you remember that you change the percentage to a decimal. You add 1, and that equals your growth factor. So your growth factor is 1.04. So for Cassie, we need, well actually, hold on, for both of these, we're going to use our exponential function, A times B to the x power. In this case, y is going to be A. I'm going to write a capital A. And B, or x, is going to be n. There we go. And A represents our, lowercase a represents our initial value. And B represents our growth factor. So for Cassie, we have A is equal to, where did she start? She started at $1,250, so we're going to do 1,250, and we're going to multiply it by the growth factor of 1.04 and raise it to the nth power. Now for Kaylee, actually, hold on, I should stick to my colors here. So I'm going to use orange for Cassie, so A is equal to 1,250 times 1.04 to the nth power, and then I'll use green for Kaylee. Kaylee started at 2,500, so 2,500, 1.04 to the nth power, and there we have two lovely equations, and you can use these to help you find find data, but also help you fill out this table. So if you'd like, you can just go straight down the line and multiply by 1.04 all the way through. So when I multiply by 1.04 here, I get 1,300. Then I can keep going. So that's 1,352. Sorry, I should have said pause the video now and fill in the table. So if you haven't, go ahead and pause the video and continue working. Oops. So if you notice, as I'm filling this out, I'm actually, so I'm kind of rounding as I go, but when I calculate my next value, I'm keeping whatever pops into the calculator. So for example, for year 5, I got 1,520.81613. Then I multiplied that by 1.04 to get my next value. So what you see here on the screen is actually me rounding my answer, but it's not the actual answer that I got, okay? So that's very important because you want your numbers to be as accurate as possible, okay? So save the rounding for the very, very end. All right, so let's continue multiplying by 1.04. So I get approximately 1,581.65, and then I keep going. Oh, forgot the decimal on my last one. 1.04, there we go. There we go. Isn't this nice? Watching college funds grow and grow. Right, almost there. Almost done for Cassie. 1779.14. So after 10 years, Cassie ends at around 1,850.31. All right, do the same thing for Kaylee's fund. So when I multiply by 1.04, I am at 2,600, and I'm going to continue doing that until I get all the way to year 10. Go multiply by 1.04 again, 3163.30, 3289.83, 0.42, 0.28, 0.61. There we go. Okay, so now we're going to try to graph. These on the same graph, and I think so. Let's go ahead and title this. So this would be the value of college funds, which they give us. So don't need to be too creative there. And then we're going to plot Cassie's fund and Kaylee's fund on here. So along the bottom, we'll go number of years. And then over here, we'll have the amount in each college fund in dollars. So labeling across the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then across the left side, along the y-axis, maybe we should go up by maybe by 500s. I think that's what we should do. So here's 500, there's 1,000, there's 1,500, there's 2,000, and then there's 2,500. I think that would be the best picture for both of these. Okay, and then please make sure you guys are labeling who's who. So the green for me is Kaylee, and then the orange for me is Cassie. All right, so let's plot Cassie first. So Cassie starts at 1,250, so already over 1,000 here, and hey, that's actually right there. And every year she increases just a smidge. So at year 1 she's at 1,300. So I'll say that's like right there. And then 1,352, not very much. So still kind of there. By year 10 she's at 1,850. So let me see what that looks like. In between here, that's going to be 1,750. So slightly above that point. So maybe like right there approximately. Right, and then Kaylee's graph. Oh no, I'm erasing. So Kaylee's graph goes somewhat like that. There we go. So this is a very zoomed in picture of an exponential graph, right? If we were to zoom out, you guys would see the exponential curve a little better. But for right now, this is okay because we need to graph both of these on the same graph here. All right, so then Kaylee starts at, oh no, actually why didn't you stop me earlier? Okay, so I need to start at a much higher amount here. Hold on. Okay, so I'm gonna start my graph here at 1,500 and then go up by 500, so there's 2,000. Or no, sorry, I'm going to go up by thousands. So there's 2,500, there's 3,500. Oh no, I liked what I was doing before. Sorry, I keep changing my mind here. So this is going to be 2,000. This is going to be 2,500. This is going to be 3,000, and then this is going to be 3,500. Okay, let's regraph Kaylee's graph then. So she's at 1,250, which is right here at 0 years. By year 10, she's at 1,850, which is somewhere between here. So I'm going to say approximately right there. I'm going to graph a few points in between just to give me the general shape of the curve. At year 7, she's at 1,644. So that's probably somewhere there. And then at year 4, let's say 1,462. So here's 1,250. So it's going to be slightly closer there. There we go. I think that's a nice picture of the curve. Okay, so try your best drawing these curves, you guys. All right, there we go. Now let's graph Kaylee's. All right, Kaylee starts at 2,500, so right there. And then she increases to 2,600 in year 1. So I'll say that's like probably right there. Then let's go to year 4, 2,924. So that's pretty close to 3,000. So I'll say that's like right there. And then at year 7, she's at 3,289. So that's just above that halfway point, because it's 3,250. And then at year 10, she's around 3,700. So I'll just graph with these points. Oops, that's too low. Okay, so let's take a look at the questions again. So it says, compare the graphs. So question number 3, compare the graphs of each equation you wrote in part 1. So right off the bat, I noticed that Kaylee's graph is higher than Cassie's. I wonder why. How does the initial value of the fund affect the yearly value increases? Well, it doesn't necessarily affect how much it's growing. because the growth factors are the same. But because of where each person started, Kaylee's graph is definitely much more than Cassie's, right? I mean, that's a pretty big difference, don't you say, from 1250 to 2500? So let me read the question one more time. It says, how does the initial value of the fund affect the yearly value increases? So how does it affect the yearly value increases? Does it affect the yearly value increases? I mean, I don't think it really does. Right? So we'll say that the initial value doesn't affect the initial the yearly value increases. Right? Because we're increasing by 4%, right? That growth rate remains the same. The second question asked, does the initial value affect the growth factor? Let's just double check that. How does the initial value affect the growth factor? Well, does it affect the growth factor? Does it change our growth factor from 1.04? No, it doesn't. So we'll say that the initial value doesn't affect the growth factor. Okay, the last part of question 4, we're trying to figure out if the initial value really affects anything. The initial value, how does the initial value affect the final value? In other words, how does the initial value affect the amount of money? Well, if you notice, Kaylee's graph is much higher than Cassie's graph, and therefore Kaylee's graph is going to have Kaylee's college fund is going to have much more money in it. So the initial value does affect, it affects the final value. Right? Kaylee's initial value was much more than Cassie's. And because of this, Kaylee has a lot more money in her college fund. So, in summary here, we'll say that the growth factor is not affected by the initial value. What is affected by the initial value is whatever our final values are, right? Or whatever our final values are, okay? All right. So a year later, Mrs. Ramos started a fund for Cassie's cousin, Matt. Dang, Mrs. Ramos, look at you. Okay, Cassie made this calculation to predict the value of Matt's fund several years from now. What initial value, growth rate, growth factor, and number of years is Cassie assuming? If the value continues to increase at this rate, how much would the fund be worth in one more year? So here we're identifying the different parts. Go ahead and pause the video, see if you guys can figure out each of these parts from Cassie's work here. Alright, so I hope you pause the video. It looks like our initial value is going to be this $2,000. Right, because we're taking that and we're multiplying it by 1.05 by 1.05 over and over and over and over. So, because we're multiplying it by 1.05, that automatically means that that number is our growth factor. Let's change it into a growth rate. So I'm going to change 1.05 into a percentage. So that's 105%. Then I'm going to subtract 100%, and that is my growth rate, which is 5%. And how many years? Well, this is 1 year, 2 years, 3 years, 4 years. And there you go. If the value continues to increase at this rate, how much would the fund be worth in one more year? So you can write an equation, you can do this on your calculator, just multiply by 1.05 one more time, right? So our equation would look like this. A is equal to 2,000 times 1.05 to the nth power, and we're at year 1, 2, 3, 4, we plug in 5, so 1.05 to the 5th power equals that, and then multiply that by 2,000. So we're at approximately $2,552.56. Let me double check my work here. So 2,000 times 1.05 times another 1.05 times another 1.05 times another 1.05 times one more 1.05, and I get the same answer. All right, perfect. All right, question C. Cassie's and Kaylee's other grandmother offers them a choice between college fund options. So option 1, $1,000 at 3% interest per year, or $800 at 6% interest per year. Which is the better option, and explain your reasoning. So at this point, I believe you guys have enough information and enough knowledge to answer this question on your own. All right, so that's it for me.